Welcome to Quantum Field Theory, lecture number 27, just to get my counting straight. We can also count to the end. I think it is -6. If -1 is the last, then this is -6. And we have still a little bit of work to do, but it's kind of fun work. It's where it really comes together. We have been talking about interacting quantum fields. While in the free theory, it was really simple to find the excitation, to find particles in the excitations. It isn't super easy to do this in interacting theory because we can't solve the equations of motion and just see what it is. So that was a little bit of work, and we basically two sides: the exact states. What we think there is, and then what we can describe more easily. What we certainly think there is a vacuum state, or the ground state, the state with the lowest energy. And we offset the Hamiltonian such that the lowest energy is exactly 0. So this doesn't have any energy and doesn't have any momentum and doesn't have any momentum, it's basically 0. It's the vacuum state. And then we have the single particle excitations, the building blocks, basically. And since the theory, even the interacting one, is Lorentz invariant, you have translation invariance in time and space, and you have energy conserved, momentum conserved, and these are all good quantum numbers, as in the free theory. So this the mass shell is still applies here. So we think we have particles with momentum p and energy p0. So they p is p squared m squared, and p vector is any number. I'm not going to go into details because it's just a repetition. So we expect these to be there. And I'm not saying how they are now created from the vacuum. They are just shaped. And then we have more stuff, which would be the multi-particle states. In the you will have two particles at the same time, right? If you want to do scattering, just a single particle isn't going to cut it. And then these many particle states can also form bound states where two or more are held together, atoms, say. And all of this is summarized in this notation, where P is the total momentum of that multi-particle state, be it bound or not, and N is all the other quantum numbers that you need. And there could be a long list, and it can be continuous or discrete numbers, whatever. Like if this was an atom, then you would have all these shells, and then so this is a lot. This is really a lot, but it doesn't matter. We can neglect all the details. The point now is that the masses are different, so they have a similar energy momentum relation, but with a different parameter here, which we just call the mass. If it's the relative momentum, it's a contribution to the energy, which we just call mass. So these are some numbers or functions of n. That's what we expect. Just moved a little bit. And here is our asymptotic states. And we had creation and relation operators. Doesn't fit here. We need to, what do you remember? Let's see if we need more. This is what we define. A of T and P, and that's 1 over this normalization. And then there's probably an I and there's an integral. I and there's the integral. E to the I x, E to be phi of x. So where did this come from? Maybe I should have written it. So the whole story is this. We have still the canonical commutation relations. Whether they're free or not, this holds. Then we can do a transformation to some, like a redefinition of our fields in terms of A's and A daggers. So basically, yeah, let's do pi and pi are replaced by this. And this is this Fourier integral. And then we have these relations. And so we have creation relation operators. And that works also in the interacting theory. What we don't know is how the Hamiltonian looks like in terms of them. It's like the Hamiltonian doesn't have to be a number operator necessarily, isn't that simple? And we don't know what the time evolution of these things is. This we can do for every fixed time, but we don't know how they change in time. Only in frequency. But this always works. And then the inversion of this, writing the A in terms of the phi's, is essentially this thing here. There are two terms. This derivative is once acting on the phi and once acting on this exponential. And these two terms are because you have basically a system of equations, of two equations, right? When you solve it. One is the phi, when it acts here, and the pi is when it acts there. I don't know. The details aren't too important. This is the that was the final expression. There was another little bit of redefinition of the phase. Yeah. And these objects and its complex conjugate partner, they create our asymptotic states. Namely, just by acting normally, right? We've shown that we define P in or out by acting with these on that vacuum at asymptotic time minus infinity or plus infinity, going really hard to do, past or future. And these P's have interesting properties which make these states appropriate for asymptotic states, namely the overlap with the vacuum is zero. The overlap with these exact states, here let's write this exact thing, is as it should be, the prime in out are these delta functions. And there's no overlap with multi-particle states, comma, prime in out exact at zero. So if with these objects we can create states which only have an overlap with these exact one particle states, then perfect. Then we have a means of creating these particles mathematically. The limit here was important for this to be zero. The overlap only disappears asymptotically. They are not good at any other time. At any other time, if you say at this morning, then it will create more than just a single particle state. It will be many particles. It will have created stuff that has an overlap with this thing here. So it's really good asymptotic only. That's where we were. And now that we have these states, we can now start thinking, not saying computing it, but start thinking about these scattering amplitudes. This is K1, K2 to KL, that's what's coming out. And in goes, here will be headline in a second, P1, P2, Pn. In. This is what I want to compute. And there's a formula that we will derive first, which relates this thing to expectation values of these field operators. That's what we need first. And that's called LSZ reduction formula. And that's the topic, 3, I guess. Yes. Yes. LSZ reduction formula. And L is Lehmann. And S is Symanzik. And Z is Zimmermann. But you just need to this. And so by definition, this thing is just what we create here, right? The bras, we have a limit of T. These are the out particles, so T out. Out goes to infinity, T in goes to minus infinity, and then we start vacuum, and then A T out K1. Then the next one, A T out K2, and so on. Then we get to the in states. Then this is an A dagger T in T1, A dagger T in T2, and so on vacuum. And now there's still this awful normalization, which also didn't make into this formula. The P's, so that this normalization which is skipped here works out nicely. There's the square root 2 EP. I'm sorry, right? This is floating around, just throw it away. And then here I can go to 2 because I've got it there. Everything is multiplied by square root, that's square root. All of these are, so the first one is in 2K1, and the last one is in 2Pn. Everybody gets the factor. This factor is going to disappear again once we insert this formula. So you might as well forget about it altogether. Now that's good so far, right? Here comes the cleverness. Like, how do we proceed? How would you proceed if there wasn't any time? Say this was a free theory, and this is all just annihilation, and these are creation operators, and this is the normal vacuum. What would you do with it? Like, strip off all the crap, and then we have A dagger, A dagger, A dagger. What would you do? Yes. What?
Alternate the A's and the A daggers till we have all the A's.
And why would you want the A's on the right?
Then it creates a 0, or
It annihilates, exactly. So we want to push them there. Or alternatively, this there. One would be enough, kind of, yeah. Does this work here? So can we push this thing there? So does this commute with this thing? A of K1 with A of K2. Does it commute? It's at the same time, yes, it commutes, and it's both annihilation operators. It does, but it doesn't gain us anything because this is just annihilating as well. And so okay. In this group, they all commute, but it doesn't give us much. They commute among themselves. It doesn't bring us anything either. So we need to go from here to there. What about this? Is this and that commute? Not very easily, because this is annihilation and creation operator, so it will be something. Do you know what it will be? Since this is T out and this is T in, you don't. These things hold at a fixed time, any time, but it needs to be the same in both. And if you want unequal times, it's really complicated to derive. We can, of course, try to derive it and proceed that way. In fact, we'll have to do something now, but at this stage, we don't know how this and this commutes. Certainly, we know it doesn't commute without any extra terms. Ah. And so, we have to be, there's a trick. This is what we know, and that works for all the t's, right? So we want to insert this, get rid of the a's, and then have the phi's. Yes. And there was a second equation that we had. We actually wrote down the derivatives of these fields. So we also had a dot t p, and this is really how we started liking them, because this was essentially the Klein-Gordon equation acting on the field, and then stuff here. And signs and so on, wonderful. Huh. No, not wonderful. This is the thing again. So this is a formula. We had this first before we had that, but you can also derive this now if you had the time, just a dot on here. Then you have time derivative hitting the t here from there, massaging, and then you'll get this. The m comes because the m sits hidden in this p0 and so on. Let's just go back and pull this from the last lecture. And now, what does that help? If you have the time derivative of a, we can easily relate a at different times by an integral. So the a at time t, say out, because we're talking about t out, for some p, okay, is equal to the a at t in plus the integral of the derivative from t in to t out. If you integrate the time derivative, then it really is the function evaluated at the upper minus the lower bound, and that's this. Bring this to the other side. Upper limit minus lower limit is this integral. So this is, in fact, I'll write it like this. This minus this is equal to that. So this will be our way to relate the thing somehow. In fact, now you could do various things. You could insert this here and replace it by the sum, and then massage. There's ways of writing this. The way that I like to write is just write down what we wish we had. So we instead of this, we want so the vacuum stays there, and then instead of a simple A be out, A1, I would like this to have a partner minus A G in of the same K. I've added this. I want. Then comes the next, which is there is right. So A T out K2, and I subtract A T in K2, and so on. And then I have what's here? I have an A dagger T in T1, and there I subtract the other time. A dagger T out T1. And then more in the vacuum. Okay, I realize there's no equal sign. It's not from this equal to this. I've just said what I want, and the reason why I want this is this difference is something okay. Well, I promise this will be okay. It doesn't look like it, but this is the way you perceive. So we want this difference. Once we have kind of argued that this is okay, then we will insert it and then go on. Now, let's see what we need to do so that this is actually true. We have added these orange terms. That's only okay if these orange terms do not contribute anything. So let's say what this does. This is sitting here to the left of all this other stuff. And if it shouldn't contribute, then it needs to really annihilate this vacuum. It needs to go through a lot of things. It needs to go through the annihilation operators at the other time. It needs to go through the annihilation operators at the same time. It needs to go through the creation operators at the same time and the creation at the other time. And there's not much good. Like this is going to give us something. This we don't even know. That's okay, and that we don't know. But now comes something really funny. People, so we need two things to happen or to invent. And the first thing is called time ordering. Time ordering operation. It's an operation. It's like the normal ordering. It's just time ordering, and it says this: if you have time ordering of a product of operators at different times, T1 and T2, those can be another one. And this means it's either A, B, or it's B, A. So this T looks at their arguments and then spits it out this way or this way around. And it always, that's his work description, later to the left. So T1 has to be later than T2. So this, or it's the other way around. Later to the left. So the earliest time, say this is 1 second, this is 2 seconds, then you don't do anything, don't change anything. 1 and 2, and 1 is less than 2, and then you leave the order, or you turn them around. This is just a definition, a symbol T. And if we what we wanted modify by adding this T thing. Around everything. then it looks at the arguments, and there's only two different times, the in and the out time, and in is before, so all the ins go to the right of the outs. This has moved this extra term past this and this. So they're out of the way, and now we're only left with this guy, which was okay from the start, because it's the same time and it's the same type of oscillator, so that it goes right through it. And so we're only left with this problem. So this thing won't go here easily through it. The time ordering just pushed it kind of, it's the same time. It doesn't really know what to do with them. And we have to be careful, you know, we don't know what it does. Same time. In this one, we need the second ingredient here, the second assumption. And that is, we will say that these outgoing momenta K are different from all the incoming momenta P. Because if they are different, then they commute. They only give a delta function. And if they're different, then the argument of the delta function is always non-zero, and then they do commute. Let me write it down first, and then say why this is okay to assume. Assume all incoming momenta P I are different from all outgoing. J. Then what we want is actually equal to this. With this extra time ordering T, which you hardly see. I wanted to have a nice red there, but I can only see it here from here. So with this time ordering, it is almost equal to that. It is exactly equal to this if you assume that they are different and this goes right through, not producing extra stuff. And then now we can actually write equal. This equals that up to the limits and the square root. Now, why is this an okay thing to assume? Of course, we can assume it. We can just say what we want to calculate here is such that all of these p's are different from all of these k's. So our choice. Well, why would we make this choice? What would be the difference if the opposite is that one of these p's is equal to one of these k's? So there's one particle which has an initial momentum, and there is one particle that has the final momentum. Since this is quantum mechanics, we don't even know who is who, and so there's one particle that's going right through. We're talking about scattering amplitudes, and this is one going right through. This is just looking at the other scatter, not scattering itself. That's a case I can ignore, because if I wanted to know, so there's 10 particles, and one of them is the same as here. Then we have 10, 10. Just forget this 10th and have 9 to 9. Compute this amplitude, because one was in spectator anyway. So that's okay. Of course, it does happen if you throw 10 billiard balls at 10. What are these things called? Kegel. Then it so happens that some of my billiard balls don't even hit a single Kegel. What's the name? I don't think it's cone, is it? Pin. So one doesn't hit the pin. So it does actually happen, this experiment. You need to know the probability that one is really just a spectator and goes along these line there. But taking this into account can be done by someone else later. It's just an extra number. Yes.
But we don't have the same amount of ingoing particles.
You don't have to have that, no.
So there could be
You could break a pin.
one ingoing momentum that is equal by, like, if there are 3 outgoing momenta that are the same as 1 ingoing? Wouldn't that mean that we ignore all 3 outgoing momenta or just one of them?
No, 1 in equals to the sum of 3.
So if there's a K1, a K2, and a K3, they are all equal to 1 P4. We ignore P4 and
Oh
K1,
dear,
2, 3.
like all of them equal.
Or do we just ignore one of them?
Yeah, just don't make it so. I think there's you have a point. There's how do you know that this was actually that particle and it hasn't done anything else? Like it has changed its spin, and it just happens to have the same mass, but it isn't the same thing. It really has to participate a little bit. I don't have a spin here. There's an extra discussion. And then, yeah, what if 2 particles have the same? All I want to say, yes, there are boundary cases which I'm sweeping under the rug. And then, these poor cases might get forgotten now, but let's say we are interested in this thing where none of the p's is equal to any of the k's. Then, well, that was accepted anyway, this is the definition, and then this is equal to this object with the prefactors. And now we can insert this down there. So now this is going to be a long, so we have K1, P1, in, out. And this is equal. Now I'm going to write the limit. I don't even want to write the limit. T out to infinity, T in to minus infinity. Then comes the vacuum. The first difference is the difference in these annulation operators. That's right here. So this comes with a time integral. So there will be an integral dt from t in to t out. And then it's the a dot. And the a dot is this from here. That first factor, the square root, will kill this. Then we have an extra I. Then we have a e3x. Then we have an e to the I dx box, that's n squared, phi hat, and then I've already forgotten my t symbol. Which needs to be outside everything. So this is the first difference there. Then comes, and that's already done because it's a P. Why did I write P? This is a K. Sorry, this is a K. The momentum here is a K. In fact, it's a K1. And then I decided K is not my favorite letter, so I'm not going to waste my favorite coordinate on it, but it's Y. So this acts on Y, and it's Y1 because also of the K2. So dy1, derivative with respect to y1, and this is y1. This is the first guy. And then comes the others, similar expressions. And the last one will be times the last one is the dagger of this. So let's take the dagger of it. Then we have a minus I. And then we have another minus sign because this is funny, the in minus out rather than out minus in. So there's another minus line. And then we have integral ut, t in, t out, integral. Now here comes my favorite letter, 1. Oh, the last one is n. e to the complex conjugate, so it's minus I Pn times xn, and then box from xn plus m squared pi hat hxn. Time ordering done. Vacuum. So here's as many of these chunks as there are these brackets, and there's as many brackets as we had particles in together in and out. So there's L plus N of these terms. Where do we continue? So again, this K1, D1 in out, it's equal. These i's are beautiful, right? Because this is minus I times minus 1, it's an I. There's just as many i's as there are particles. So this is N plus L. The next thing, if we, there's this in out, this is from minus infinity to plus infinity. This is combined beautifully with this thing. We should have also probably given the t a different name, because this is the time component here. This is the time component in so you just go on, right? The oscillator had an exponential factor, and there was a time in there. That is this time that is in the argument of the oscillator. And the same time is also here in this argument. So it is the zeroth component of the y, if you wish. And this combines beautifully to d4y. And let's write it like this. Let's write it as d4y, and then there's several of them with an index, and with a product j from 1 to L. There are L many of these. And this together is a 4-dimensional integral. Then we have an e to the I k j y j. Or then I have a box y j plus m squared. And all of this, right? So this is all the product. We have one for each. Then we have more. Only for the incoming. And d4 xi e to the minus I ei times xi box xi plus m squared. So that is now all of the ones here. And this is acting on vacuum time ordering by the first one, let's say, it doesn't even matter which is the first one, because time ordering will take care of it. So let's say we have y1, because it wasn't the first one there, and then to yl, and then x1 to xn.
Why were you able to push the time ordering to the
How did you know? That's exactly the what is it? The problematic case. In general, it is not an allowed step, because time and time, right? Time ordering here, there's nothing to I could have written. So first, let me say the problem for everyone. This thing can be written as a sum of these two terms with theta function. So you could say theta T1 minus. Do you know what theta is? How it's defined? Everybody? Theta?
Yes.
Theta of -2?
Yeah, it's negative, it's just 0, and it's positive, it's 1, or like some constant you find. Often as like 1/2.
When it's 0.
Oh, I mean, no, it was like -1 and 1. For negative, it's just -1. For positive, it's 1, right?
That's not theta. That's the epsilon. That's the sign thing. If you here theta of x, I want switch off, switch on to 1, as you said in the beginning. And then you said, oh, 1/2. So sometimes at equal to 0, then people put it as 1/2. I think that's a very clever definition to have it 1/2 there. But we don't worry even about the case when they're equal. So with this definition, we can write that as a T1 minus, no, T1 B T2 plus theta T2 minus T1 B T2 A T1. And now it's clear that if you take the derivative of this thing with respect to T1, say, from outside the time ordering, that's not the same as if you had the time order, the derivative for T1 in here. So the T1 hits the A operator, not the B operator. So it looks like it just hits here. However, if you spell this thing out, there's a T1 there and there. And it'll hit the theta functions as well. And not just this here, this product rule, and there's the terms that you would get if it was inside, indeed, but plus extra stuff. And so therefore, you can't just move derivatives with respect to time in and outside. And that's what I did here, because this is the box. It's D'Alembert, it has a second time derivative, and it's the time associated with this coordinate, the space-time coordinate, which is time order there. So and here suddenly it's outside, and I pull it out, and that's not allowed. However, in this combination, second derivative and this equation of motion, and then I integrated as well, and not just differentiate, makes it good in the end. And that is apparently, been trying to answer exactly this question for a week now, and all the books kind of neglect this. People don't even tell you that they've done something funny. Schwartz, in his book, if you want to look at like standard model and quantum field theory, Schwartz, he says this step is not allowed, but it'll be okay. And so then I tried to dig into it, and we would have to spend weeks to work this out. And it is actually like you credit these three people for this very non-trivial work that we don't really all write down. It's super technical, and it'll be good in the end. You will have terms that don't, like the ones that we neglected. Two p's being the same. See, why is this? Because it hits the theta function, and the derivative of a theta function it's a delta function. So the delta function sets two things equal, 2 times equal. That's a so it also is something that coincides. People call things that coincide contact terms. So now you have 2 of them basically at the same time. Like it was here, we excluded the cases where the p's are equal to the k's. And now there's a similar story to exclude the same coordinates. You know, you have things that are bad if they coincide in quantum field theory, because then you have deltas of zeros and divergences. And so after a very, very long technical story, the terms that we have now dropped by this unjustified step aren't gonna contribute. So after having thought about it for a week, how to tell you, you were a bit faster now, I decided to just do the step as well and to tell you that there's something fishy, but it's going to be good in the end. Yes, you know, it's the sixth to last lecture. Let's do something fun. Yes.
Sorry, I don't really see where we put the derivative in. So what I see is like we put the limit inside the time order.
Yeah, well, the limit could also wait for a minute. The problem was this derivative here, it has a time derivative in it, moving past t.
Where did it move past?
Here. The boxes are now outside the t. I have this expectation value in the vacuum of these operators time ordered. And once I'm done, I'll take the derivatives.
Okay, yeah.
But what this formula said, don't take the vacuum expectation value yet, just do the derivatives, time order them. Then if it is not.
And we also put the limit inside, right?
Well, let's say this came out and then they. There. Sorry. Now this is a pretty formula. This is LSZ formula. It's in coordinate space, and it means it's just that. You have to compute for the scattering amplitude. You compute a time ordered expectation value of the fields. You have to have so many fields as you have a sum of in and outgoing particles. And then when you're done, you have to do this to it. And we want to now figure out what this is. Because this can be made even prettier. This looks a bit like, what does this look like to you? E to the IPX integral over x. Fourier transform. And Fourier transform for what? Of these x's, like this thing here. And then this is opposite. Aha, so of this acting here, it's a Fourier transform. If we got rid of this thing, or, you know, this is a derivative. We can Fourier transform this as a factor. So let's do this. Here. We have integral e to the minus I p x box dx on some function. Then we can integrate that parts twice to the other side, every time a minus sign, on this thing. And this box gives me a minus. There's the result.
Ich habe zu engagiert darüber diskutiert. Ich habe zu
Yeah, it's my
engagiert die
fault.
Flasche geworfen.
I thought about this integration by parts because there's another thing. Well, where are my surface terms? So the surface terms are still down the drain. Everything's supposed to fall off, it's in here and here, no. So I pushed it there, second derivative, and then you have d for x minus d squared I dxf. So instead of the box, I could also just put minus the corresponding p. If this is xi, then I have to put pi. So the formula can also be written as I n plus L, and then product I1 to n minus pi squared plus m squared product J1 to L minus kj plus n. And then it's the Fourier transform, and then we call this G of P1. I call this, what is it? We have integral. If we define G tilde of P1 to Pn as D4 product from 1 to n, E4x, e to the minus I p I times x I of omega time order phi 1, phi x1 is phi xn. If you find this thing, this is now a definition. This is the Fourier transform of this time ordered correlation function. Then we could write this formula by inserting here the p's, p1 to pn and minus k1 to minus kl. Here I wanted all the same letters. So even for the outgoing y's, there are now x's. That's why the index runs to capital N. Capital N is little n plus L, these are now all of them. And it is just one sign here and they're all p's. But if I want to use it in this formula, then of course I have to switch some of the p's to k's. And the k's come with a different sign, with a plus sign. So I have a minus in there. So down here is the Fourier transformed, time-ordered endpoint correlation function. This is the time-ordered endpoint correlation function. This is the Fourier transform of it. And the scattering amplitude is the Fourier transform time-ordered endpoint correlation function multiplied by this stuff. What is this stuff? How much is this, for example? What is pi squared plus or minus pi squared plus m squared? What's p squared? The 4 vectors squared. See, if you have a p squared, do you remember what this is? Like this is the p0 squared minus p vector squared. What's p0? The energy, right? How much is the energy? It was p vector squared plus m squared, and then minus p vector squared. So it's just m squared. So p squared is m squared. The p without an arrow, the 4 vector, is m squared. Yes?
And all our particles have the same mass.
Yes, it's the Klein-Gordon here, they have all the same mass.
And all
It's
the
this
same.
model.
Okay.
We can do more complicated things and then they're all different, yeah, and then if you want to. You have, then, you know, if it's more complicated theory, then you have to specify more than just the momenta. You could, for example, then the spin, the polarization, if they are dark spins, or if it's many species, you have to specify the species. And with different species, you're gonna have issues with different masses. These are all the same species, and therefore they have all the same mass and charge 0. So what does that tell you now? P squared is m squared, and here we have minus pi squared m squared. What's saving you? What's the I? This is 0, right? P squared is m squared minus p squared is the minus m. This is 0. 0 times 0 n times the whole thing is 0 to the n plus l. It couldn't be less than that, I guess. It could be one more 0, but this is pretty 0. The whole amplitude is 0. The probability that anything's happening is 0. All right, see you tomorrow. No, what can save us? How can we get a finite answer despite these many zeros?
We have some
Who's-
infinities.
Who's brave enough? You are brave enough. If this thing is infinity to the n plus l, you'll have something finite. So this is telling you, this is the answer. So this is just awfully divergent. It's just, and it's divergent when the p squared is the m squared. These are the zeros, right? If this is not the case, p squared is equal to m squared, then that's not a 0. Funnily, that's exactly this is the case that we need, right? Our particles that are scattered here have an energy momentum relation, which is this. And so then we have this ill-defined expression of 0 times infinity. So what we are supposed to do now is compute this thing for generic for generic p's. Generic means the components. So it's p mu I. These are the, you know, p0, p vector, all of them. They do not. They're supposed off. We call it off shell. So p0 is not equal to EP. Don't impose it. Just think mathematics rather than physics. These are just 4 vectors. So use generic 4 vectors, boom, of shell. And then we'll get an answer, which is finite and beautiful. And then the formula, LSZ formula, tells you you don't even need to bother about all the terms. Just keep the ones that are really divergent, the ones that will become singular, if you changed from off-shell to on-shell momenta, if you go away from the generic to the really particle momenta, then there will be divergencies. And from those divergencies, keep only the coefficients, basically. Yeah. So it's like this. You have someone gives you a formula for your answer, A's answer, and it says limit for x to 0, x times g, right? So this thing. Then you say, oh, x is 0. Then my answer is 0. No, if this has a pole, right? And what you really need is then to find g of x should be something over x plus other. You have a think of a Taylor expansion or Laurent expansion with a pole here. And then what this formula tells you, pick this number. This is the answer. So your Fourier transform Fourier transform endpoint correlation function will have some poles like this. It won't be an x, it will be a p squared minus m squared in the denominator. And this formula above here tells you just throw this away, multiply by the denominator, multiply by the thing that goes to 0 here, and just keep the coefficient, the residue, if you want to call it like this. And now, of course, you are worried, I can tell. What if there is a x squared? Huh? You know, then, I mean, if this wasn't divergent enough, the whole thing is 0. If it's too divergent, then the whole thing blows up. And we are still not happy. We want to balance. And there's a theorem, if you have a unitary theory, if it's all good, all physical quantum field theory, then you won't have these too much divergence. Quantum field theory 2, I guess. Yeah. I haven't proven this. It's just, it comes out just right. You can, if you had Feynman diagrams yet, you could make this statement with a picture, and then you see where these come from. So all these particles, they will be lines, 3 in, 3 out, and then they do something. And so something is happening with all these lines. And so every line brings a divergence, and then there's so many as there are lines, and so you know you can kind of almost see then that it works, balanced, not too divergent. Then, yeah. But this is all just rough, and this is kind of the general direction. Lots of things to be discussed. Here is our formula. What do we need to do? For computing, yeah, this is what we want to do. Scattering amplitudes, these are these overlaps, these scalar products, and here's your formula. Go and compute the time-ordered correlation function. At some point, I'll drop the H's. These are the Heisenberg picture things. So this is the whole story for now. How to do this? But once you've done it, then Fourier transform it, read off the residues. That's your answer. So next topic has to be computation of these time-ordered correlation functions. Yes. 7.4. And that's hard. So we will do free theory first, just to learn how this works. There's no several steps. What do you like to see? See, time order. Hard. So, but this thing is what we want to compute. And in this section, to go small steps by small steps, we say we look at free theory and only 2 fields. 2-point correlation function. And that's already interesting enough. So we want to compute vacuum time ordering phi x, phi y. And here I'll give this thing a name. Do it now. Well, d f x minus y. It's called Feynman propagator. But it's just a name. This is what we're going to compute. And we'll see why this is why it deserves a name and where it's coming from and where it's going. for us, it is an example for here, for the, you know, it's really just a very, very first baby step. It isn't even any useful because it would mean as a scattering amplitude of one particle to one particle. But one to one, even in interacting theory, this is one going, it'll have its own momentum and we've excluded that. So this building block is even, it's a building block. It's by itself isn't going to give us any amplitude. Yeah. And what is it? We can spell it out again, because we've learned this. It's x0 minus y0. If x0 is larger than y0, then the order has to be phi of x first. So it'd be phi of x and phi of y. And if it's the other order, y minus x, then it is y first and then x. And if you wonder what if they are the same, then I here said they are not the same. Different points. So I don't even have this problem to answer. For different points. Its divergence is the same. Now, we have a name for this already. Do you remember what that was? What was phi phi? Without the time ordering, we didn't know what time ordering was. I'd be most happy if you told me not the name, but the interpretation. I tell you the name. It's d x minus y, right? Yes?
Are you looking for the word
Micro causality? One second, are we still recording? I guess we are, right? And now the question.
How did the omega state become the null state?
How did it? Because this word. So yeah. I could have written it here. In the free theory, our vacuum has just been 0. We don't know how to deal with it. In fact, this omega will be a whole series of states. And we'll next week, I guess we won't do it tomorrow. We will convert them. Here, I'll just look at 3, and so this is the free vacuum, and these are the free fields with the mode expansion. Yes.
But generally, omega was like the lowest possible state, or what was it defined as?
Omega is the lowest energy state, and then we put it to 0, but it's not the 0. Well, in the free theory, the 0 is the omega. It's the same thing. That's why I could replace it. Now. I wanted to know what the P was, what this thing was. And indeed, we had it when we talked about microcausality. We had the commutator, so this order and the other order, and then we could write it as this and this thing. The interpretation though was, this is a coordinate, this is the closest to a coordinate eigenstate. This is the particle at position y, then this is the particle at position x. And if you have x, y, this amplitude means what's the amplitude of propagating from x to y, being at y and then going to x. And then we saw, if this is a space-like separation, these two things are the same. Like in general, d of minus x is d of x complex positive. And it's not necessarily the same. But if the argument is space-like, then it's a real function, and then you can change the order, and then they cancel. And we said, okay, microcausality is valid because there's particles from x to y with an equal probability as from y to x, and in the commutator there's negative sign cancels. So that was there. But here, mentioning this, because we have the same object, and so this Feynman propagator means the amplitude to propagate from the earlier to the later spacetime event. While the d means from that to this one to this one, the t looks which is first. So it's kind of more physical if you want. It's you just throw them in, you just give me two names, and then the t says you'll always propagate from the first to the second, like in time order. And that's what it is. This is like the idea with this case, positive or negative time difference. And now we need an expression for it, like math. We have an expression for the d. The d was this thing, an integral over e 1 over 2 dp e to the minus ip x. This is what we had earlier, what we remember. We got it really just from 0 and then inserting the mode expansions and then have these oscillators and commute, and then this is what was left. Minutes. So this object, the d, is just even if the time here, y, happens very, very late. You still keep that order and you have the sign here. So always, if I have x and y, then I have to put x and y here, and then there's also x and y. If it's just x, it's like having the first one at 0. And this guy satisfies an equation. You know what's this equation? What's the equation in x? The differential equation in x. I'm not getting this. What is this? P with respect to x. Oh, if you, yeah, right. You can act with this thing. Sorry, exactly. We've done p squared, and then p squared is, it's really minus because of the I, and blah 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 0. You could do it this way by looking at the momentum, this Fourier expression, or by just applying the differential operator to this expression, there's the only x. There's no time ordering which bothers us, so we can just pull it through here. And this phi satisfies the Klein-Gordon equation because I'm talking about freeze here, and then you get 0. Either way, you get 0. So this amplitude, propagation amplitude of propagating from y to x, satisfies the free normal Klein-Gordon equation. What does our Feynman propagator satisfy? So if I boxed as m squared df, what do I get? And so, yeah, that's complicated, right? Because here, there's time. We need to hit it here and there. And then on this propagation amplitude. Do it slowly. How many derivatives and particles can you do at once in the head? 0, then you won't get anywhere. Well, let's do 1 at the time then. Okay? So with respect to x0, we'll differentiate with respect to x0 the Feynman propagator. Okay? So it's going to hit this thing, turn it into a delta function. Delta x0 minus y0, then we have dx minus y. Then we have plus this. This makes it as well a delta function, but then you have an inner derivative of minus 1, so you get a minus. Do we agree? Right, now then, chain rule, in front at once. So delta y0 minus x0, and then dy minus x. This is when it hits the weird terms. And then there's the normal. So plus normal. I don't even want to write them. What does normal mean? Plus theta x minus y d x minus y plus theta y minus x d y minus x. Now, what is the first? Let's look at the first only. That's symmetric, so it's delta x0 minus y0, and then d x minus y minus d y minus x. The d was this expectation value, so what I get is delta x0 minus y0, 0, phi, x, phi, y, and the other order, commutators. That's the first line. What do you say about this thing? How much? Zero. Because this is at equal times and they commute. In fact, they commute also non-equal times. 0. Yay. So the extra junk is gone. We have only the normal. Let's hit it again with the second time derivative, x0 squared on df. Now we have to differentiate this thing. Sorry, who was not paying attention? I wasn't certainly. These fairness, you were paying attention, but you weren't sure whether I'm. Yeah, thank you. So the derivative has to be this thing. So dx0 dx0. No, God. dx0 dy minus x. Now, first the terms on the theta function. That's then dx0 dx minus y minus delta y0 minus x0 dx0 dy minus x plus, and now I can't forget the second derivative, dx0 twice plus theta y0 minus x0 dx0 twice on dy minus x. The first line is going to be something Q2. It is delta x0 minus y0, and then there's again a commutator because it's the same, but the commutator with the derivative on the x0. So it's going to be what we had before, phi of x and y. However, with a time derivative on this one. And we know what that is. Yeah.
I have a question first. If we like the zero above in the orange line, yeah. I obviously see that the commutator is zero, but if we multiply it by a delta function, are we still sure that it's really stays zero if we have like some infinity there?
Now we don't trust anything anymore, right? Because any zero could be multiplied by an infinity.
Yeah.
It's my own fault, right? Why is this zero a better zero than the other zero, right? I mean, should we keep any zero now? What is this? This is. I mean, what is this multiplying? What are we doing anyway? This is you know, at some point you have to say there can't come another infinity. I mean, this is we're working here, right?
No, I'm just asking, like the delta inside our expression already. Is this a one that's like, yeah, we can really multiply it by zero, or it just like we have a delta to the left of our expectation value, and it's like same times. Would we still be sure that this is zero? But maybe if x0 is y0, then
Oh yeah, X isn't, they weren't supposed to be at equal places anyway. However, you know, you don't set x0 equals y0 and then have delta of 0. What you could do is integrate over them, and then in passing, basically, in integrating, they can be they can become equal just as an integral. That's how the delta function is supposed to work, right? It's good under an integral. If you don't integral, just insert values, it just doesn't do it. The delta function is not to be evaluated, it's integrated. And this I would allow myself to integrate, but I don't want this delta to be infinity times 0 giving me something finite. What is this thing now? What is by dot? It's pi without dot. It's not 0. But what is it? This is the pi, yeah, that's the pi. And pi with pi is, and then it could be, you have to decide is it plus or minus. So it is the delta that we had from there, x0 minus y0, then it's a minus I because the pi is in front, and then it's delta 3 x vector minus y vector, and this combines beautifully to a 4-dimension. So this is minus I delta 4 x minus 1. This is what the first line is. The second line is what the second line is. Now we have here prepared it, just the time derivatives. This, however, is time derivative minus space derivative. That's the first thing. And now, but space is not so bad because space goes right through the time ordering. Where's my formula? It goes right through this here. It only hits that. So what we get is all the unexpected terms, 0 plus this. So it's minus I delta 4 x minus y. And then comes plus when it hits on the normal terms, basically. But the normal terms are 0 and then box plus m squared on phi. Oops. I'm ordering. Yeah. I was gonna write it short, so where here the Klein-Gordon operator hit the field phi, there wasn't any time ordering. Now it hits the field phi as well, which is hiding under the time ordering in the Feynman propagator. And we have extra terms which we worked out, and we know the extra terms. This now is 0 because this is 0. So this is kind of the naive way of getting 0, but that is the extra pieces. So, that's 0. And now you have this. We have a solution to the Klein-Gordon equation, which has a 0 on the right-hand side, and we have a solution to an equation that looks like the Klein-Gordon equation where someone put a delta function on the right-hand side. Have you ever seen this case where somebody puts a delta function on the right-hand side of a otherwise homogeneous equation? Yes, you know. And why and where?
Green's function.
Green's function. Yeah, Green's. And this one is so beautiful. And that's why the Feynman propagator is also called a Green's function. It is technically a Green's function. And then people call the whole thing, the whole correlation functions, Green's function if you want. And so what is a Green's function? I'm just going to tell you what a Green's function is, and then we're going to stop. If you have a differential, so you have a linear differential equation in x, say, and that's my differential operator L. It acts on the function of x, and it's inhomogeneous, linear and inhomogeneous. So there's a given function here, a given differential operator, and you're looking for a function f as a solution. And now somebody else gives you a Green's function to this. So if you have a solution, like Green's function satisfies this equation with a delta function on the right hand side. Then f on x, the one that you, so what then I should write more words. Then a particular, it's not your general solution, a particular solution is given by f equals integral g x minus y rho of y dy. This is like really pretty. Let's try it out. Check if Lx acts on this f of x. Since it acts on x, not on y, I can just pull it to the integral. And then I have integral Lx and g x minus y rho of y dy. And here's the only x, so it only eats this. But L of g is by definition delta. Now it's not g, it's g minus x, but that just means this thing is delta x minus y. G minus x, I have to go home. It's g of x minus y. So this is integral delta x minus y, rho of y, dy. And that evaluates to rho of x. And that is what we wanted. We wanted f to satisfy LF equals rho. So a Green's function to an equation, a differential equation, linear differential equation, is a function that satisfies this and can be used to produce a particular solution to an inhomogeneous equation when you're given the inhomogeneity. You just have to write this integral. So that's why this is generally interesting. And here it's just a fact that this Feynman propagator, the function that we want to study in this section, just as the simplest example of our time ordered correlation functions, it's a Green's function. So we wanted to know and learn, what does this t now do to us? Without we had it, and now we want to get all of them. We want to find all of them. Here's our first example, and now we see what the t does. The t changes the function from being a solution to the homogeneous equation to this Green's equation, the one with the delta function homogeneity. And tomorrow we'll use this knowledge to find an expression for it, like solving this equation. And yeah.
I have a question exactly for this equation. How did you get the second box?
The second box.
Or the
this
box on the right side. In the
this box.
Yeah.
Yeah.
How did it result from the?
So here I took the box apart
Yeah.
into time derivatives and spatial derivatives. And then there's also this m floating around if you take the whole thing. And now we applied it. I applied this space, oh, gone.
Yeah, but that's all fine.
So we did this, and we found extra terms, and we found things where the d acted on inside. And the others don't produce extra terms, but act also here inside. And then I could put everything together very quickly without telling you in this. Yeah, I guess you have to write it all down once. It's many steps in long equations. But morally, it's very simple. This is a simple two-point function x and y, and the derivatives here, hit there, and Pythagorean is satisfied. If you stick a time ordering in, then you produce a little time dependence, and then the time derivatives here produce something extra, and it doesn't actually produce a net one. So it's pretty. It comes from time ordering. Yeah. All right. Thank you for today.